Hello guys, Assalamualaikum and good morning. So I'm going to continue with the lectures that we have missed. So we begin from the chapter on Planck distribution. We have not quite finished this chapter, so I'm going to start from that. So essentially, remember we start off with the idea of black body radiation, which we model through a cavity. So again, how we model that, we think of the electromagnetic radiation actually given by standing waves. So what I'm going to do next is essentially to think of the energies that's being absorbed by the black body wall consists of oscillators. So what we have recall a result from quantum mechanics on harmonic oscillators, where the energies are given by the following, which is n plus a half h bar omega. Okay. And essentially over here, we're going to make this dependent on k because we want to make the connection with the wave number. So essentially, this will now represent the black body radiation sort of forming standing waves in the black body cavity. So now essentially when you have n equals to naught, we have this half h bar omega in the context of harmonic oscillator. So these are known as 0-point energy. But we're going to ignore this. Will be ignored. So the other thing that one has in this particular case is that we have this quantum number n. So essentially in harmonic oscillator, it's just giving the level of energy. But now your n will be instead of a quantum number, it will be the number of particles. Or in this particular case, the black body radiation is going to be coming from photons. So these are bosons. Okay. So if you have more bosons, then essentially what you're going to have is that your energy will be increased. Okay. So, and we would like to look at get this thing up a bit. So we want to look at the average number of particles. So this will be given by n, and then remember we're making all this thing dependent on k, so this will be having dependence on k, and this is just given by your ordinary statistical formula. It's just the number of particles in each what you call levels. It should come in a minute. Okay, n equals 0 to infinity, and your probability is now given by your Boltzmann kind of distribution, and h bar omega coming from there. Okay. nh bar omega, which is now dependent on k, divided by kbt, divided by essentially your partition function. So let's now write down our partition function. Now this depends again on your k. So there will be from starting from n equals 0, that means you have 1 there, and then n equals to 1. So I'm going to ignore omega as a function of k there. It's understood. So and so on and so forth. This is for n equals to 2, and further terms for which you can combine. This is a geometric series, so this will be giving you 1 over 1 minus e minus h bar omega, okay, putting back the function of k there, kbt. So okay, so coming back to the average number, so now you plug it in, average number of particles here. So you plug in your z, so that gives you n bar k equals to, oops, I don't want that, n bar k equals to sum n equals 0 to infinity n e minus nh bar omega function of k, kbt, and then remember that you have the divided by z. There is now this which is in the denominator, being reciprocal there, so you bring it out. Now the problem is now is to sum this. Now to sum this we need a particular trick. So let me just write down the trick. When it's sum, use following. And this can be written as taking the derivative, bring out the n there. This is sum e minus nx, sum of n, and then this is again just a geometric series, so you can write down the answer for that sum. So that is 1 over 1 minus e minus x. Then that would actually give you e minus x over 1 minus e minus x squared. So then you plug it into your average number of particles. And that should give you the following: e minus h bar omega k on kbt divided by 1 minus e minus h bar omega function of k kbt squared, and then the factor that comes from z. So we can simplify that to give the following. Need just another step, sorry. So I have E minus H bar omega K on KBT. The square has been cancelled there. And then you divide top and bottom by this factor. That gives you 1 over A H bar omega K KBT minus 1. So now we come to the point where we should be able to compare this with what we had before, which is, let me just check. Yeah, earlier when we talked about Planck black body radiation, Planck distribution, we had something similar with as a function of lambda and t. So here the dependence here is on the wavelength, and for this one is actually on the wave number. So we're going to have to do some conversion here. This is the one given before. Now, in order to convert the lambda into omega, so that is comparable to the one above, one has to remember that side here for photons is omega equals to ck. In the ordinary sense, we have this new lambda thing. Okay, then one can actually make the replacement there. You have to check this for yourself. This will give you h bar omega on E h bar omega on KBT minus 1. So in other words, one can think of the Planck distribution is now given by the oscillator model. So this is an essential thing that we want to do. Okay. So your black body radiation can now be modeled by oscillators. Okay, that let me clear up this screen so that I don't have to push everything up. So now remember what we had was essentially for a particular wave number. So generally we want to consider all possible wave numbers. So in other words, we sum over all k to get your, this would be your, like the total thermal energy. So U bar sum, why is bar? Because we are involving the average number. So you have h bar omega multiplied by n bar there. In other words, we have the average energy, and then you sum it over all possible k. Now, of course, this is going to be, remember that essentially you can have a continuous k, so one would like to turn this into an integral. And in order for us to do that, then we need to involve density of states. Okay, so the density of states for 3 dimensions, we have actually done this in terms of wave number. It's given by this volume, in this case the volume of the cavity, over 2 pi squared k squared. So if I want to do the sum, then I'll replace this as an integral bar here, and then we have this factor of v on 2 pi squared. Just make that working. I think I should make this a bit more pointed, so that's better. 2 pi squared, and then you remember the thing that you're summing. So this will be h bar omega k n bar k, and then the factor of k squared coming from the density of states. And this is sum from 0 to infinity. Okay. Now, that should be giving you the average total energy or thermal energy. Now, let's try to do free energy for the black body radiation thing, so that we can calculate all other thermodynamical variables. So your free energy, we try to use partition function instead, since we have already worked this thing out for particular k. So in this case, we need to sum over all possible k. So you remember we have a factorization thing. So on and so forth, where your zk, let me just rewrite that, is given by your Planck distribution here. The Planck distribution usually is the one with the other factors coming in. So now what's your free energy? Your free energy is now given by this. So this being under the log, and the partition function is now a product. So this becomes a sum. So, and we already have the formula for zk. So let me just put it in. Sum k log 1 minus E minus h bar omega on kbt inverse. So again, this is assuming like you have a discrete k. So turn into integral again. So again, when you have a continuous k, you have to remember that you need to use your density of states again. That gives you kbt. The minus sign over here is going to be cancelled out from that inverse there under the log. Okay, so that gives you integral from 0 to infinity, the density of states, times the log of 1 minus E minus h bar omega k on kbt times dk. Remember, we have removed the minus 1. So having done that, we need to be able to determine what omega k, and remember omega k is given by or maybe not yet. Okay, not yet. So let me just point out another thing. So here you have your k squared over here. That well, your dk will have k squared, and then you have your v on 2 pi squared. This is coming from the density of states factor. So k squared log of 1 minus e minus h bar omega k on kbt dk, and then remember we have the factor of kbt in front. So kbt here. And then we have to remember another thing that we have to remember. There are two modes in your black body radiation. It's an electromagnetic wave, so there are two transverse modes. So we need to modify this with this describing the two transverse modes. Okay? So you have that. So now we need to be able to how to integrate this, and the other thing that I mentioned just now is we need omega equals ck. So how to integrate this? We use integration by parts. So in this way you can consider, for example, remember integration by parts from school. You have this integral given by uv minus v du. So we need to identify what's dv, what's u. So u, we take it to be your log. And then your v is taken by well, dv in this case. dv is taken by k squared dk. So when you integrate this dv, you get a factor of 1/3 k cubed. So I'm not going to go through all the steps. So let's see what happens over on uv. uv will give you something like this. So remember, this is taken from 0 to infinity. uv is 1/3 k cubed log of 1 minus e. Then I'm putting in the omega equals ck, so I'm putting here h bar ck on kbt, and then all of this is taken at 0 and infinity. Now for 0 is clearly 0. At infinity, what happens is here you have an exponential minus infinity, and that again is 0. So that term is gone, so you're now left with minus v du, which I will now write the following for your free energy: minus v kbt over pi squared v du and this is equal to minus 1/3 v kbt pi squared, and then remember we have to do some change of variable there. kbt integral of k cubed Okay, coming from that k cube there. Just write it down first. Give it t minus 1. Now, for this, we need to make some change of variable. So we write z equals to h bar ck on kbt. And if you do that, then you can rewrite your f as follows. Putting all the substitution in. And where possible, you sort of simplify things. Use a factor of 4. So we have the integral here, z cube. Write that properly. Z cube divided by ez minus 1. Now, what we're going to do, we have to look up some table of integrals, or you can do it in Wolfram alpha. We have seen it before how you do that. This will be giving you pi 4 over 15. Okay, that integral. So we can now rewrite the whole thing as minus pi squared kb 4 t to the 4th h bar c to the 4th here, cancel with one of this h bar c on the numerator there. So that will give you h bar cube c cube, and then you have the factor of 15 over here, multiplies the factor of 1/3 there. That gives you 45 here. Pi to the 4th cancels off with pi squared to give you pi squared. So essentially, this is the free energy that one has for black body radiation. Okay. So with that, as you can see, now we have the free energy. We can now calculate your entropy. So entropy is related to your free energy through this formula. And we can differentiate this easily. So that gives you 4 pi squared and kb 4 t cube v on 45 h bar cube c cube. Now we want to go back to the idea of the average thermal energy, and this is again related to your free energy in the following way: U bar equals to F plus Ts. This comes from your thermodynamical formula, and you can just plug in all the answers that we have, and that gives you pi squared kb to the 4th t to the 4th v over 15 h bar cube c cube. Now what else one can actually do is we can also find out the pressure of the black body radiation. Okay. So this is given by P equals to minus the F dV, which is now easy for you to differentiate that, that gives you, say, pi squared kb4 t to the fourth divided by 45 h bar cube, c cube. And then you compare this what we have for the average thermal energy, then you can actually rewrite this as u bar over 3v, and you can see you get this familiar formula for the radiation PV equals to 1/3 u bar. Okay. So right, before, there's a few more things that I wanted to do for the black body radiation. One is the Einstein model for oscillations and solid, and also the device model. I will continue this with another recorded lecture after this. Okay, that's all for now.